Okay, we are starting the recording for this lecture. Welcome to the Q learning and DQ and algorithms, and with famous frozen lake example to illustrate these two algorithms. To start our discussion here, let's remind ourselves where we are in the map of the reinforcement learning algorithms. We are in the optimization algorithms for model free, and we are talking or discussing the off policy algorithms. And basically, we have two flavors: the Q learning and the DQN. We're going to use this example, the famous frozen lake example, and basically what we have in this example, we want to start from this position and get to the our goal here, cross the lake, and these tiles or squares represent the lake, and some of those squares are frozen and safe to step on. We can go here safely, and some of these squares are holes. The ice has melted, so or is thin. We can step here, and you will fill in a hole here, so it's not safe. So we have to learn our way to get from the starting point to the terminal, avoiding these holes. Now, we don't know these holes, by the way, okay? And as you can see, an agent wants to cross the frozen lake. The lake is divided into 4 by 4 squares, 4 by 4. The agent should start from the starting point, right, and reach the goal. And only stepping on the frozen squares and not stepping on the on top of these holes, because it will be terminal hole and we have lost the game. Okay, the agent can make one of the two moves. The agent can go up, down, okay, right and left, okay, at any square. Um, Also, agent doesn't know the holes, as we stated, and doesn't know where the frozen square, or doesn't know where the goals. Okay, this is obviously clearly we need model-free reinforcement learning method. Agent is required to cross the lake, oh, there's a typo here, from S to G. It has to learn the safe way itself, okay? When it goes from here to here, to crossing the lake, it has to learn it itself. So really our objective is to enable the agent to safely cross the lake without falling into one of these holes. Okay, and the agent has no prior knowledge of the lake where the holes are. Clearly, it's a model-free reinforcement learning method here we should use. Okay, so back to the frozen lake. Reinforcement learning objective is to generate policy to safely cross the lake. The figure shows the example policy. Now, the policy here, basically, it gives me directions. So if I'm in here in the starting point, the S here, I could go to the right, and or I could go down here. If I'm at square 4 here, obviously if I have an optimal policy, clearly I can go up, but that's not optimal. The optimal for me is to go down. And if I get into 8, clearly I can go to 12, but I will fall in a hole, or I can go to 4 and I will go away from my destination. It will be further from where I want. Clearly the optimal action is to go right. So you can see these arrows represents an optimum policy, and this is where we want to get. We want to get to these arrows, these directions, and to get to this policy, clearly we need to run one of the model-free reinforcement learning algorithms. So policy includes actions to safely cross the lake. Some squares have one safe action, like 4 here, square 4, and some have 2 safe actions, like for example 9. You can go to 10, square 10, or you can go to square 13. And clearly we have numbered these squares, by the way, by numbers, so we can easily refer to them. Again, our objective to enable the agent to safely cross the frozen lake. The agent has no prior knowledge of the lake. Okay, now Of course, we need to solve this problem. We need to formalize the problem. Okay, we need to introduce the notion of actions, Markov decision process, etc., and then employ one of the algorithms that are model free algorithms. And in this case, off policy algorithm. In this case, we're not going to use on policy, and Q learning, deep QN will be discussed on this example. Okay. Now, all right, so let's formulate the problem. Clearly, I have those as my states. So we will add the following components to the problem: rewards. So now I'm going to attach rewards to go into all these states, and my rewards are zeros. But if you get to the goal, I'm going to give you a reward of 1. Okay. Now we have states, right? And these states are enumerated from 0 to 15, 0, 1, 2, 3, as we'll see in the next slide, or I have seen in a previous slide. And we have 4 actions in any state. In any of those states, right, there are 4 actions. Okay. We're going to consider the goal as terminal state, and so are those holes. They are terminal states, but I'm going to terminate with a loss. I did not cross the lake. Okay. All right. So here is our reinforcement learning system. We have an agent, try to maximize the future rewards, right? And events are going to move from by steps. Some of this material really, I'm repeating what I have discussed in previous slides, but it doesn't hurt. Events in each step are ordered, of course, and at each step, the environment emits the my state or the observation and the reward. Okay, so this is going to my agent, and the agent makes its move by issuing an action. Okay, and then we move into the next step. All right. Okay. Now here are the states. Okay, and for my algorithm. Or let's talk about a policy. A policy defines a behavior of an agent. Okay, so given a state, all right, it tells me what action I should take. So for example, if I'm in state 0 here, which corresponds to this state, clearly I have and those are the actions: left, down, right, and up. Those are the actions. So this table really, the rows are the states, the columns are the actions, and the values here are the action values. So if I'm in state 0, which action I should be taking? Well, clearly down and right are the top 2 actions because of their action values are the highest. So I can go down or I can go right here. I have a choice because they are equal. If right, for example, has a value of 0.9, it means I have no choice. But if I'm looking for the optimum policy, I have to go to the right. But in this case, they are equal values. So this table, we refer to it as the action value table, or the Q table in the Q algorithm, the Q learning algorithm. Now, so a policy defines the behavior of an agent given the state S and what action it should be taken. Okay, so basically here we have probabilities of taking an action. So when we say the policy says, the policy pi says the probability of this taking this action is 0.5, it means if I am in state 0, right, given state 0, then the probability of taking action, for example, down is 0.5. Okay, all right. I can say that assuming these are the probability. But of course, here I just indicated to you that this is the Q value. So let me not point to this table while I'm talking about the policy here, because I'm going to confuse it. Those are the Q values. But let's go back to this. So the policy is the probability of taking an action given a state. So if I'm in state 0, I'm not going to point to the table here. If I'm in state here 0, so the policy tells me what is the probability of taking to action right, what's the probability of taking action down, action left, action up. Okay, all right. So this is basically the policy as we discussed in previous classes. So the figure shows an example policy on a state and table that lists the probably. Now this is of course now will be later referred to as a Q table. Now the Q table here are they become the action values. Okay. Okay. I'm gonna here repeat an earlier discussion of how to compute the action value and the state value. This is a discussion that has been covered in earlier classes. So you can look at it and review it. For the sake of time, I'll just say this is how to compute the action value for right given state 14. So if I'm in state 14 and I'm taking action right, okay, how do I compute it? Okay, and how computing the state value. So this is the definition, and we've discussed in earlier classes how to compute the action value using state values, or the state value using the action values. So this is repetitive of earlier classes. Okay, so I'm gonna just move on quicker on those slides. Now, the optimum policy is better than all other policies, and this is our target, because typically when you run these algorithms, you would hope that you get the optimum policy, which minimizes the moves, minimizes the cost. We want it to be better than typically the optimum policy is better than any other solution. So optimum policy is the expected value of the total rewards over successive steps is the maximum achievable. Well, this is clearly because, after all, reinforcement learning maximizes the rewards. Okay, optimum policy is associated with optimum. So when I have an optimum policy, it means my state values are optimum, my action values are optimum as well. Okay. So, and somebody would say, okay, so the algorithms, the Q learning will work on what? It will work on the action values. But once you find out the action values, you can compute the state values, as we have discussed in earlier classes. We know that. Okay. Now, so let's so for the Q learning algorithm pseudocode. Now let's go to this Q learning algorithm now. We initialize all the Qs in the Q tables, or Q values in the Q table, to 0. We initialize the learning rate, okay, so this will be given. And for each episode, all right, so now we will run through episode, basically from a state, we still go take an action to the next state, to the next action, to the next state, to the next action. And the question is, how do I pick the next action? It's based on the epsilon greedy policy, which we'll talk about in a second. So we reset to start state. We initialize the reward list to empty. For each time step, we choose an action. Okay. And of course, we'll talk about the exploitation trade-off. And we observe the reward, and we execute this update equation. So the update equation is what? Well, the new value of the action A from state S is the old value plus learning rate, and open those two brackets. We have the target minus the old value of the action. And in the target, I will get this reward. Obviously, when I take this action, I got the reward from the environment. And then I take the maximum value of the actions of the destination. Okay, and we'll see how this is being done in the Q table. Now, if I reach the terminal states, then I'm done with my episode, and I go to another episode. Now, here we will use decaying epsilon. Okay, and this is epsilon times e to the exploration decay rate, should say. Actually, there is a typo here, times the episode number. Okay, now if I get here, all right. So here is my Q table. Again, states, lefts, and these are the Q values. So the Q table stores the Q values for each state action. Each states represent a row, okay, as we explained. Action are represented by columns, and the dimension of the table is number of actions times number of states. And you can tell immediately we will have a problem in these tables for situations where the number of the states or the number of the actions is huge. Okay, so all the state values in the table are first initialized to zeros. Over time, the Q values produced in the state pairs in the state action pairs that the agent experiences will be used to update the Q values. So in the update equations, we will update these values. Okay, and which is this one here, the state action. We will update those as we train this model. As the Q table becomes updated in later moves and later episode, the agent can look in the Q table and base its next action on the highest Q value. So for example, once I'm done from this table, I can training, I can go to state 9 and see which is of those highest action values and pick my action. Okay. Now, so here is an example of a table where we have done training. This is when the training has completed. All right, you can see clearly here for state 0 here, what are the action with the highest values, down and right. So my optimum policy is to go to the right or go down. Clearly, going up is not optimum and going left is not optimum because their values are not the highest. Okay, so let's take state 1 here. I can see from this the action values which action has the highest. It is right. So from state 1 going to the right is the optimum move. Clearly it is actually. Okay, going down is not optimum. I will fall into the hole. Going up is not. To the left is not. So, and how about state 2? State 2, you can see all these actions. The maximum action value is this one here, which is to go down. So from when I'm state 2, the best direction for me is to go to because this will give me closer to the path to my goal. Okay, get me closer to my goal. And how about 13, for example? 13 here, the highest value or for when I go right. Okay, when I go right. So 13, the best action, okay, the optimum action is to take a right action, okay, to the move to the right. How about 14? This one to the right. So the best action is to move to the right and I will reach my goal here. So this is the table that comes out of the Q learning algorithm. And from this table, I can generate my optimum policy, which action is the optimum that I can take in any of these squares, in any of these states. Okay, so this is the product, the final result, okay, of my Q learning algorithm when I apply it on the frozen lake. Okay, very important here when I take my next action. If I am in a state during the training, if I'm in a next state, how do I decide on the next state? As we mentioned in the last class, we have the epsilon greedy policy. This epsilon greedy policy has epsilon and greedy. And epsilon motivates take random action. And greedy, it motivates exploitation because it says take the action with the maximum action reward. Okay, so what should consists of epsilon, okay, which says random, greedy, which is 1 minus epsilon. So if epsilon in my algorithm is 90%, so 90% I will take random action, and 1 minus 90%, which is 10%, I will go for the greedy action, which is to take the action with the maximum reward. Okay, so exploration, right, is exploring or discovering the environment to find out about it and using random moves and action. And exploration is very useful during the start of the simulation, in the early stage of the simulation, because I don't have any knowledge of the system. So I would maximize this to be very close to 1, so that I will do a lot of exploring. As the simulation moves, right, and I have run many episodes and I start discovering this system, there's no need for to have high random value. There is no need to have 90% of the actions to be random. Now I can decrease them because I have built a knowledge about the system that I can take some good actions now. So when I'm choosing one as epsilon, okay, I'm really motivating exploitation, which is the act of exploiting the known information about the environment in order to maximize the return. So I do both, right, in during training. However, I will do more of the exploration in the early training. I will do more of the exploitation in the late stage of the training. So exploration with no exploitation, well, of course, you really not utilizing the information that you have built. And exploitation with no exploration results in not discovering a better and a greater returns. It is important to balance between the two. And the epsilon greedy policy tries to do that. So at the beginning of the simulation, as we said, we focus on exploration, and the algorithm, as we execute the algorithm, okay, and we gain more knowledge about the environment, we shift to emphasis gradually from exploration to exploitation. Okay, so the epsilon greedy defines the exploration rate as epsilon, okay, and which is the probability that an agent will explore the environment. So we'll say, if we say epsilon, we set epsilon to 0.99, it means when I take an action, 99% of this action will be picked randomly, okay, which is good at the beginning of the simulation, right? But if I say epsilon is zero point 0.1, when I take my next action, then 10% of the time it will be random, and 90% of the time I will pick the action with the maximum action value. Okay, and this is appropriate once I progresses too many steps and episodes in my simulation, not in the beginning. So if epsilon close to 1, the agent will explore the environment, clearly because it does many random moves, and if epsilon is close to 0, the agent will exploit the environment knowledge. So initially we set epsilon close to 1. This means the agent will start exploring the environment. Makes sense. As agent learns more about the environment, epsilon will decay by some rate, okay, and that's why we decay it, so that the likelihood of exploration becomes less, and the agent will become greedy in terms of exploiting the environment by choosing the best action, which meaning the action with the highest values, and we do this gradually. Okay, so it is as if we move the needle from the maximum randomization to greedy, exploration to exploitation. Okay, high value of epsilon to small value of epsilon. All that, yeah, okay, means the same thing, right? Okay, so how we generate this in a programming environment? You can generate a random value from 0 to 1. If r is less than epsilon, then you really doing the exploration step, which means you choose a random action. If r is greater than epsilon, then you really doing exploitation, which means your next action is the action with the highest action value given the state that you are in. Okay. Okay, how about the deal about learning rate? We talked about it more in the past. So after determining, so the next action, the q value function is updated as follows, as we talked about it earlier. This alpha is the learning rate. Okay, alpha is the learning rate. One thing worth mentioning, if alpha is close to 1, all right, it means that the new value is set to target, and we are ignoring my old knowledge. Okay, and if alpha is close to 0, it means that your new value of the action value is set to the old one, and ignoring the target. So you have to be careful of what you want. Really, you want to keep the old value, right? And you want to learn from the new target. Okay, so you have to balance this act. Okay, so once we take steps in an episode, sometimes in these random moves, we can take forever in any episode. So you have to set maximum step per episodes, and if you reach that maximum, you auto terminate. And this is with a reward of 0. Okay, so. Okay, the number of episodes determine the number of episodes used in learning. This is you set it in your program. Okay, let's take a look at how we update an example. This is my update equation. Let's say, for example, I had the discount of 0.99 and have a learning rate of zero point 0.7. Assume my current state is 6. So this is the table here. These are example values of my action in my Q table. Assume we are doing exploitation, meaning my next action will be determined by those action values. Obviously, this is the highest action value, so I need to go down. So 6 here as a state, I'm going down. To what state? State 10. Okay, so hence the action is down, and the action is Q state 6, action equal down, and this is 0.6. This is my current value. Now we calculate the maximum action of the next state. So I'm going to state 10 here. What are the actions for state 10? So I look up in the Q table here. What are those actions here? Okay, what's the maximum action value? It is 0.9. I need in the update equation. So now I'm ready to run the update equation. The new value for state 6 taking action down equal the old value, learning rate times the reward, okay, plus discount, maximum value of all the actions value for state 10 minus the old action value for state 6 down. Now, plug in the numbers from what we discussed. Q6 down 0.6, alpha is 0.7, it's right here. The discount is 0.99, it's right here. The maximum of all these values here is 0.9, so I plug in a 0.9 minus the old value of this one, which is 0.6 as we said. Plug in the numbers, and now the new action value for a state taking action down is 0.8037. So this value here will be plugged in right here in the table. And this is just one update equation in one step in one of the scenarios. Okay. So the limitations of Q learning is this algorithm works beautifully, but it is efficient as long as you have a relatively small state space and a number of actions are manageable. But if you have a very large space, a state space, then the performance suffers in complex environment as can be predicted. In this example that we looked at, we have 16 states and 4 actions. That's 64 Q values. So it's easy to compute those 60 Q values. As number of states increases, really the time to update the Q values would increase, and it becomes unmanageable for complex systems. So what's the solution? Well, using Q table and this update equation, we can do a functional approximation or a functional approximation, and none beats the performance of a neural network. So now we will, for complex problems, we'll take out the Q table and the update equation and plug in their place a neural network. Okay, so deep learning, deep Q learning, and deep Q network, which is DQN. It's deep Q learning. It is really deep neural network with Q learning. That's what it is. We take out the Q table and we put a deep neural network. So we employ a neural network here, and we will approximate the deep Q learning is a deep neural network that approximate the optimal functions. And this one I'll see in a second. So somehow it is equivalent to the update table and the function update function. Okay. So how is this deep Q learning, which use Q neural network? The function of it approximates the optimal Q functions and estimates the Q values. The structure is a deep neural network. The input are the environment states, and the layers are the convolutional layer here, and with all its related layers. Okay, so we can see that how this Q table now will be approximated with this neural network. The states become the input layer. The actions here, okay, become the outputs from this neural network, and we have to train this neural network so that it produces these values here, those action values. Okay. So the Q learning computes the optimal Q function by iteratively updating the Q values using the Bellman equation. This is that's in the Q learning algorithm. But here in DQN, what we replace this by saying this DQN approximates the optimal function using deep neural networks. So basically, we are approximating this Q table with the neural network. Okay, so the output of this neural network are these action values. Okay, and basically those are we are approximating those values, and the loss function that we are using here. So the loss is the difference between the output Q values and the target Q values from the right side of the Bellman equation, and we'll see in the next example how that happens. Okay, so the objective of this neural network is to minimize the loss, and we will explain in the next slide what is the loss. Okay, so, or maybe the slide after. Okay, now, so DQ training, when we talk about training, we need to explain few terms here. First is agent experience and experience replay and replay memory. Agent experience is a summary of the behavior experience. So you see, we are talking here about off policy here. So obviously off policy, we have a behavior policy, which from it I will derive my experiences. Okay, remember the example of the last lecture. We said that the behavior policy is that somebody, a second person riding a bike, and I'm sampling from that person these samples, right? So that I can improve my own policy, the target. I am the target policy. So agent experience is a summary of a behavior, observed agent experience at step time. So when we observe this behavior policy, I will sample experiences, call them ET. From that, I will sample the state, the action that behavior policy took, and the reward that was generated by the environment, and the next state. Now, experience replay is a store. So I'm going to store all these experiences in an experience replay to store those experiences. And typically to sort the agent experiences at each step in a replay memory. Okay, so I will store those experience replay. Basically, I will put those experiences in a replay memory so that I can do a experience replay, meaning I will take them one by one so that I can use them for my training. Okay. Okay, so all these experiences are saved in a replay memory, and number of those experiences is n. Okay, so now, so here is my replay memory. Okay, I collected these experiences. I watched the second person ride the bike, and I collected these experiences. Now I need to train my memory, my neural network. This is my neural network, right? And this is the neural network that is supposed to give me from its output the action values of a given state. So I present the state to it. It's supposed, after training, give me the actions for the states. And now I can tell from each action which is the best action. Okay, so now during the training, I will pull experience by experience. I'll take this experience. I'll say, for this experience with a state ST, so I'll apply ST to the inputs. All right. And then watch what I'm trying to minimize here. I am trying to minimize the loss function. And the loss function is what? The loss function is the difference between the reward plus the discount times the maximum actions coming from the next state minus those action values. So let's see how we will do this in training. Once I take an experience, I will present this state in the experience as an input here. Then from the output, there will be the actions, the action values for the state. Okay, I will pull which action values of these. Well, I will pull the action value that corresponds to this action in this experience. So this experience tells me take one of those actions. Let's say for A1. So it will say here, for example, A1. I will take this A value and plug it in the equation. And then the experience itself will tell me the reward. So I will take the reward here and I plug it in the loss equation. Then what about here the maximum the maximum of all action values of the next state. So I will take this state here and I plug it in one more time here, and I will have bunch of actions, and I take the maximum of them and I plug them here. So in this policy network, I will use it twice, one for ST and one for ST plus 1, which is the next state. So the same network will estimate for me the QAs and the maximum for the next state. This method, right, of using one policy network can lead to instability in simulations. So what people did, they separated these two networks, right? One is the policy network and the other one is the target network. The policy network produces for me the QA right here, which is coming from the current state, right? And the target network, we will use it for always for the next state, the ST plus 1, and we will pick the maximum action and plug it in here in this equation so that I can compute the loss, which is used to train this network. Again, why did we separate them to two policies? I can always use this ST to plug ST plus 1 and plug it in here and get these actions and get the maximum and plug it in this equation. But I'm doing this second neural network so that I can have more stability in my simulation. And every once in a while, I will copy the policy network into the target network. I will sync them, but not every step, every once in a while. Okay, so now policy network, which I'm trying to minimize its loss, which provide for me the QAs, and target network, which provide for me the maximum action of the next state. Okay, and I will do this for every experience, and then I continue pulling up those replay experiences from the memory and train my neural network. Okay, so this is the algorithm, and I've already talked about all the steps of it, but this is okay. Again, why two networks? Why two networks? The policy network output the estimated value, the QAs, and the target provides the optimum actions of the next state. Using one network can result in instability, but however, two networks stabilizes better the simulation. With that, with this slide, I conclude what we have started, which is basically the target of our session is to give you an example of the frozen lake example and an illustration of in using the Q learning algorithm and how we can move from Q learning algorithm to DQN. I hope it was a useful lecture for you, and thank you very much.